Okay, sorry about the technical issues. Hopefully third time's the charm. As we were heading out, in terms of the computer freezing, I had asked a question in terms of how do we integrate x e to the x. And so I'm wondering, has anyone gotten any ideas on how to actually perform that integration? Okay, so I don't see any responses just yet. So in this case, we're going to use what's called integration by parts. So we're going to let u equal to x and then du. Oh, good. Alexis, so with that delay, you probably set it in time. Shoot me an email. You get a bonus. That's an eagle eye right there, or an eagle bonus there. So go ahead and shoot me an email reminding me after this, and I'll give you a bonus for it. So du equals dx, or dv equals e to the x dx. And then the antiderivative of e to the x is just e to the x. So we're in good shape there. Alright, so keeping all that in mind, what do we have? Well, this becomes, the limit as t approaches negative infinity. Then it goes uv, so if you have minus v du, and then what you start with is u dv. So that's our formula if you don't remember the integration by parts formula. So now, writing this out, it goes uv, so that goes x e to the x, evaluated at t and 0, minus the integral from t to 0 of v du, so that would be e to the x and then a dx. Okay, so we've used our formula, and we know that antiderivative of e to the x, so we're in good shape there. We get the limit as t approaches negative infinity of x e to the x evaluated at t and 0 minus e to the x evaluated at t and 0. So this equals now, limit as t approaches infinity, we can plug in the 0 in the t, so you get 0 times e to the 0 minus x, or in this case t e to the t. Okay, and so from there, what do we have? We'll have this, and then minus e to the 0 minus e to the t. Wowzers, right? Trying to write all this out, the 0 will go away, but an easier way for us to deal with this, you can write the second term as t over e to the negative t, which will be useful to us in a second, minus 1, and then minus, we'll do another limit I'll write right here because we can figure this out too. Limit as t approaches negative infinity of e to the t. As t approaches negative infinity, notice that number is going further and further negative, meaning this will be 1 over e to the some power. This thing's going to 0. So this part is going to 0. And welcome back to your limit laws, because notice now when we plug in negative infinity, you get negative infinity over e to the infinity, which is infinity. So you can use L'Hopital's rule. So that's what we'll use on that first case. So we have a limit as t approaches negative infinity now of 1 over negative e to the negative t, and then minus 1. So in that case, notice that is now approaching positive infinity down the denominator. So that means the whole thing goes to 0. So this whole part goes to 0. And so we're left with negative 1. So that means that this thing converges. Okay, since we actually evaluated it. This will pop up later on, not necessarily towards negative infinity, but if you have to go on and take a differential equations course, things of this form, times e to the x dx, so like x e to the x, things like that, we'll have to figure out solutions to on these improper integrals, and they're very beneficial to us. So now moving on to the next thing. This is something I saw multiple times in the discussion boards, so I want to make sure we address this. It's actually determining this error bound. What the heck is going on? Where's the main importance? So in terms of what we want to do is usually we want to find how many intervals do we need in order to get a good approximation. That's the whole idea of this stuff, is how many do we need? Because usually you'll have some sort of software running that program for you. We just want to know how many intervals do we need for it to be efficient. Okay, so whoops, I skipped one there. All right, so sorry about moving forward there. Now, with that in mind, what we have is the trapezoidal rule. The error bound says that the error, this e of t, right, for the trapezoidal rule is less than or equal to b minus a cubed. Now what the heck is that? And then divided by 12n squared times m, where f double prime of x is less than or equal to m. Oh, okay. So I got a question here on number 2, and I'll hop back onto this in a second. So number 2. Let's see. The question states, for number 2, where did the 1 plus cosine of 2 theta go in the beginning? So are you talking from here to this line, I'm assuming? So where did it go from there moving on down? Just give me some clarification there real quick. Yeah, so no, I'm glad you're asking the question. So the question was from here, at this point, moving on down, I used a property, basically a plus b times a minus b. It's a difference of squares. So that equals a squared minus b squared. Your a in this case was equal to 1. Your b was equal to cosine of 2 theta. Whoops, not cosine. There, cosine of 2 theta. So where that came from is just combining those two in that difference of squares format. Okay, does that make sense then? I know you said that you see that I combined them, but that's all that we did, is just recognize that that's a difference of squares. So good question. Keep them coming. You got them. All right, so back to the error bounds. So with this trapezoidal rule, you have this e of t is less than or equal to b minus a cubed over 12n squared times m, where f double prime of x is less than or equal to m for all x, where a is less than or equal to x. It's less than or equal to b. Okay, well, here's the deal. Not to be confused with the problems a and b, but a is your lower bound, b is your upper bound. Okay, so that information is given to you. Now, in our case, what is this? This is our error. So that's going to be our e of t. Now notice we need to find a bound on that second derivative. That's where things get a little bit tricky. So we have our function f of x equals e to the x squared. That means f prime of x, just using the chain rule, should be 2x e to the x squared. That means f double prime of x should equal, well, we got to use the product rule now, and we get 2 e to the x squared, I believe, plus 4x squared. Is that right? E to the x squared. So notice that means we can simplify that a little bit. You get e to the x squared, and then we're left with 2 plus 4x squared for that second derivative. Now let's keep that in mind. Okay, so when we do this, what are we left with? Well, you can kind of check. Well, actually, I'll kind of fill you in on Simpson's rule first. By the way, Simpson's rule, very similar. The error bound is going to be b minus a to the 5th over 180 n to the 4th times m. Now, where f triple, or we have 4 primes, I'll write it this way, where the 4th derivative of x is less than or equal to m for all x in that interval. Good. I see another question on problem 2. I'm going to go back to that right after we finish this one, if that's all right with you. Let me know if that doesn't work, but hopefully that way I can finish up this problem and then kind of move back to that then. All right, so taking a look at, we have equals e to the x squared 2 plus 4x squared. To solve both of these all together, we're going to need a third and a fourth derivative, so I might as well do that. The third derivative we can get to be e to the x squared times derivative of 2 is 0, derivative of 4x squared is just 8x. Okay. Plus, our next one would be e to the x squared times 2x times 2 plus 4x squared. Okay. So notice when you simplify this, you get a 4x here plus an 8x cubed. So this becomes e to the x squared. 4x plus 8x would make 12x plus an 8x cubed. So now we're ready to move on to our fourth derivative. Okay. So fourth derivative, what's happening here? We end up getting the first part of our product rule. Take the derivative of the second part. You get 12 plus 24x squared. And I'm running out a bit of room here, so I'll move that just slightly below. And then for that next part, we get e to the x squared times 2x times 12x plus 8x cubed. So notice that means our fourth derivative, and now we have all four derivatives that we need on this, equals e to the x squared notice we'll get a, let's see, the 12 will remain the same. Notice when we multiply 2x times this, we get 24x squared. Okay, so plus 24x squared. And then the 2x times the 8x cubed would be a 16x to the fourth. Okay. The reason why I mentioned this, this integral in particular, because we don't have normal means of integration. You can't use a u substitution, you can't do an integration by parts or any of those to actually solve this one. Now the other thing you can kind of notice is actually that the second derivative, we'll start with this, so we'll deal with the trapezoidal rule. We need to find a bound such that f double prime of x is less than or equal to m. Now the nice part about this one, if you plug in the function, let's see, you can plug in 0, you notice you get 1, and then you get 1 times 2 in there. But when you plug in 1, notice you get e times 2 plus 4e squared, right? So what happens with this, you can see by the second part, you're going to get on the interval 0 to 1 only positive integers or positive numbers, 0 being the worst case scenario on that interval 0 to 1. So with that in mind, that tells you that this function is increasing. So the f double prime is increasing. So with that, we have f double prime, since this is increasing, f double prime of x is less than or equal to f double prime of 2. Or not double prime of 2, f double prime of 1, which equals e to the 1 squared times 2 plus 4e squared, which means that's just going to be e times 2 plus 4e squared. So that is our m value. So when we plug this in, we get e of t. Well, that is going to be 0.0001. Oh, we only want 0.001, sorry. So 0.001. We want that to be our error bound. We know that on a and b, we have b equaling 1 and the a equaling 0. So you get 1 minus 0 cubed divided by 12 n squared times m, which that is our bound. So it's e times 2 plus 4e squared. Now here's the whole trick to this. We want to try and solve, and hopefully I can erase, I'll put it actually up above. Okay, so we want to solve for n squared. That tells us how many intervals do we need? How many things do we need to break up our problem into? So with that in mind, multiply both sides by n squared. Notice you get 0.001. Then you divide both sides by 0.001. And you're left with n squared is less than or equal to 1 cubed divided by 12. Then you have e times 2 plus 4e squared. And down below we have that 0.001. Okay. So what happens? Well, we can get this in a calculator. Okay, you'll get some number. To give you an idea, and then where do we go from here? Wait, did I make a... Yeah, n squared. Sorry, I was double checking my work. I had a little writing mistake. Yeah, so when we do this, we can actually solve for and my apologies. A little caveat. With this, I said e of t is less than or equal to, which is the truth. But I want this error to be less than 0.001. So my apologies here. In terms of that, if I want the error to be less than, we know that error is always less than this value with the bound. But so I noticed that this could be the maximum of the error. And so in this case, I want to actually reverse this process to greater than or equal to. The reason why is because this is always going to be our maximum attained. This is the worst case scenario, is 0.001. So usually it's e of t less than or equal to. If you're calculating the error, that would be the bound on the error. Well, as long as we make this larger, then we're going to be in good shape. And so just verifying that little error, because I wanted less than the 0.001. That's a worst case scenario. If we make this worst case scenario less than that amount, we're going to be good to go. So now, and if you do have questions, please let me know on that. I'll fix that real quick for you. So notice this means n is greater than, since we're dealing with positive numbers, is greater than or equal to 1 divided by 12, and then times that 0.001 in the denominator, and then we have 2 plus 4e squared. Okay. And so now we can take a square root and see what this is approximately. So notice that would be, and this would be if you ever wanted to use a calculator, this would be the place to do it. So if you plug that in, you'll get something around the ballpark of 51.28. Now with that in mind, trapezoidal rule, what does that mean for n? Well, n equals, in that case, if it's 51.28, n we're talking intervals, number of intervals, you need to be a whole number in that case, so we have to round up. Because if we rounded down, that would mean a possibility of having an error of greater than 0.001. So that's the trick on that part. Now the same rules are pretty much going to apply on the second part for Simpson's rule. But we need to do the fourth derivative. Okay. With that in mind, same thing, you can check and see that this function is increasing over that interval. So the maximum here occurs at the fourth derivative at the point 1, once again. If you plug in 0, you'll see it doesn't hold. So now in this case, oops, I don't need the absolute value there. What happens to equal here? Well, in this case, you'll get e to the 1 squared is 1. Well, I'll plug it in just so you can see that. 12 plus 24 times 1 squared plus 16 times 1 to the 4th. And so what does all that equal? Well, 12 plus 24 plus 16, that's 40, 52, I believe. So that should be 52e. So this one's a little bit easier to have as our finished product. Oh, wait. Did I make a mistake on that last one? Yeah, I did. My apologies. I made a huge mistake on the last one. I said 4e squared. Let's revisit that real quick. I just noticed that. F double prime of x that should have not been an e. I put the e in the other spot. My apologies. That should have been a 1 there. So this should have been just a 6e. Sorry, I was getting ahead of myself doing double duty. Got to focus on one problem at a time. So let's go back here. It won't hurt for me to redo this one real quick. So that should have been 2 plus 4 times 1 squared, which is less than, or, well, which is equal to 6e. Okay. So notice when we go, we get n squared is greater than or equal to 1 cubed divided by 12 times 0.001 times 6e. Okay, hopefully I'll stay a little more focused on this problem and finish it off. My apologies on that real quick. So now, actually working this out, we can get n is greater than or equal to, and so n does not equal 52, by the way. We'll fix that real quick. N is greater than or equal to 1 divided by 0.012 times 6e, and we take the square root of that. Okay, so 12. And so now this answer, which is the correct answer, is 36.87 essentially. So that means when we round up to the next whole number, you get n equals 37. Sorry if I caused any confusion. I got a little ahead of myself there. And hopefully this will be cleared up on this one. So we have 52e on the second one, on the Simpsons rule one. So now when we take a look at that, we have a similar scenario. We want to do 0.001. We want it to be larger than that possible error. So that's a worst case scenario. So this error, oops, we have B and A are 1 and 0. Divided by a new number here, we have 180 n to the fourth times m, which we just found is 52e. So a little bit more interesting there. So notice we get n to the fourth. Hopefully we can see that on the screen. So n to the fourth is greater than or equal to 1, and then we have a 180. 0.001 is what we're dividing by, and then times 52e. And in case you can't see that just yet, there we go. Hopefully that looks a little bit better now. So now, what do we get? We get the fourth root of both sides, so you get n is greater than or equal to the fourth root of 1 over 0.18 times 52e, which is approximately, let's figure out what that is. And so hopefully if we've done this right, usually it turns out your Simpsons rule is going to be much more efficient. So in this case, you get 5.29. And now Simpsons rule, you also have to be careful. It has to be that even number, if you recall, when you're taking a look at that. So in this case, with the 5.29, luckily when we round up, we get n equals 6, which should do the trick for us. Questions on that one? Okay, so the question that was occurring during that one, let me go back and address it. It said, in problem 2, where did the 1/8 come from? So let's see if I can find that. Okay, good. So I think the reference to 1/8 is this 1/8. Am I correct on that? So let me know, just verify that. I believe it's that 1/8, not the next one, because hopefully you see that that 1/8 just carried on to the next step. Now notice we have 1/4 times this integral. So what happens is, when we take 1/4, it goes times this integral. And then we take 1/4 times 1/2, which was times that. So the 1/4, when we went and multiplied by 1/2, that's where we got the 1/8 from. 1/4 times 1 is 1/4, which is what you see right here, and we pulled that out in front of the integral. 1/4 times 1/2 is 1/8. That's where that 1/8 came from. Hopefully that makes sense. If not, let me know. I just want to make sure that you have that down. And all right, let's get back to it. So now a few more. These will be a little bit more challenging, I guess you could say, in terms of what we're dealing with here. So we have an integral of e to the 5x sine of 2x. Okay. What do we actually use? Well, you have some options in terms of what you could call u, what you could call dv. In this case, let's call u equal to e to the 5x, and du equals 5e to the 5x. That means dv equals sine of 2x dx. And v, if you take the antiderivative of that, I believe you get negative 1/2 cosine of 2x. If you want to try and check and double check and make sure, if we take the derivative of this, what do we get? Well, you get negative sine of 2x times the negative 1/2, and then times the derivative of the inside, which is 2, and that would cancel off, the negative cancel off, and you're left with sine of 2x, so we're in good shape there. So what does this make? Well, this makes u times v is going to be e to the 5x times negative 1/2 cosine of 2x minus v to u, so that's minus, and then, well, I'll just leave it in there for now. Negative 1/2 cosine of 2x times du, which would be 5e to the 5x, and then a dx. Gonna toss in that dx. All right. So let's brush that up just slightly. So we're left with negative 1/2 e to the 5x cosine 2x. Minus minus makes a plus. You have a 5 and a 1/2 makes 5 halves. And then we have an integral of e to the 5x cosine of 2x dx. Okay. Continuing in the same pattern, I'm going to use u1 and dv1. If we let u1 equal e to the 5x, that means du1 equals 5e to the 5x dx once again. Same thing here now. If we go dv1 equaling cosine of 2x dx, and that means v1 is going to be sine, 1/2 sine of 2x. If you don't see that, you can use a u substitution and hopefully get there. Good practice for you in terms of what happens. So this becomes the negative 1/2 e to the 5x cosine of 2x plus 5 halves, and now we'll have a new integral. It goes u1 times v1, so that'd be e to the 5x times 1/2 sine of 2x minus an integral of v1 du1, so it'd be minus the 1/2 sine of 2x 5e to the 5x dx. Let me close it off. Wowzers, right? So I'm going to bring some attention to what's going on here. Notice I do have some constants there, but I have an e to the 5x and a sine of 2x. I started with an e to the 5x sine of 2x. That's important because what we have is we have the original integral e to the 5x sine of 2x dx equals negative 1/2 e to the 5x cosine of 2x plus, if you multiply this 5 halves times each part, here's what you get. You'll get 5/4 in that first scenario. 5/4 e to the 5x sine of 2x. Then minus 5 halves times 1/2 times 5. So 5 halves times 5 halves, which is 25/4. Times the integral. So this is e to the 5x. I'm going to write it this way. Sine of 2x dx. So notice now, making a minor change, I'm going to put this in black. You have one of these over on the left hand side. and you have negative 25 over 4 of those on the right hand side. So what we can do is we can add this whole amount over to the other side. So notice of those e to the 5x sine of 2x integrals, you get 1 plus 25 over 4 times the integral e to the 5x sine of 2x. And that, oh, let me toss on the dx. That should equal negative 1/2 e to the 5x cosine of 2x plus 5/4 e to the 5x sine of 2x. Okay. So now 1 plus 25 over 4, though, that's just 29 over 4. Just get a common denominator. So we have 29 over 4. And so notice, if we multiply both sides by the reciprocal, what are we left with? We're left with the integral of e to the 5x sine of 2x dx equals, multiplying by the reciprocal will be 4 over 29, and then times all this stuff, negative 1/2 e to the 5x cosine of 2x plus 5/4 e to the 5x sine of 2x. And you can simplify that some more, and we'll toss in a plus c. But we've solved using integration by parts, and notice we used it twice, kind of move things back on over to the other side. That's a tricky case, but it's something that pops up from time to time. Don't worry, I'll address it again soon enough. So now another trig integral, tangent to the 5th, secant to the 5th dx. So tangent to the 5th of x, and then secant to the 5th of x dx. How do we integrate this thing? Well, we're going to need some trig identities, and you actually have some options here, and I'll kind of illustrate what some of our options are. You have an option tangent squared x plus 1 equals secant squared x, or you could do tangent squared x equals secant squared x minus 1. Either one you can kind of work with. In this case, let's try and get a secant squared x out of this. Well, notice you can write this as tangent to the 5th x. We can factor out a secant to the 4th x times the secant x. Now, why would we want to do that? What's the whole purpose here? Well, notice we have a secant, and the derivative of, well, in terms of what we're looking at, there's a couple different ways we can approach this. Derivative of secant is secant x tangent x. Derivative of tangent is going to be secant squared. So we actually have a couple different options here in terms of what we're dealing with. Which one are we going to go with? So actually, let's do this a different way. Not the secant to the 4th. Let's use the tangent one. That'll be a lot smoother here. So in terms of this, we can write this as tangent to the 4th of x. And then we'll have an extra tangent x sitting on the outside here. And notice it'll allow us to have the secant x tangent x that we're looking for when we have derivatives of secant. So now tangent to the 4th of x, we can rewrite as tangent squared of x. Then we square that. And then we can write the secant to the 5th of x as secant to the 4th of x times secant x tangent x dx. Okay, so tangent square we just mentioned using this identity right here. We have this is secant squared x minus 1 squared secant to the fourth x, and then we have a secant x, tangent x dx. So notice at this point you can say u equals secant to the, or u just equals secant x, du equals secant x tangent x dx. Well, if that's the case, notice we now have, this might be a little bit easier for us to work with, u squared minus 1 squared, u to the fourth, and then we have, notice all this, rather than dividing it this time, I'll just write it as du. And in order to do this, we're going to need to expand the square. So we have, this becomes u to the fourth minus 2u squared minus, or plus 1, times u to the fourth du. And notice that equals the integral of, just multiply the u to the fourth on through now, u to the eighth minus 2u to the sixth plus u to the fourth, and then all that du. And we can kind of use that reverse of the power rule, and we have our antiderivatives are u to the ninth over 9 minus 2u to the seventh over 7 plus u to the fifth over 5 plus some constant c. And we know that u is secant x, so we're left with secant to the ninth of x over 9 minus 2 secant to the seventh of x over 7 plus secant to the fifth of x over 5, and then plus some constant c. And that's our final answer. Okay, so hopefully you see how that works. With tangents and secants, you just have to use different trig identities. So there's all sorts of trig identities. You're going to use them one way or the other. Trust me, I'll be challenging you on that. Okay, for our next one, square root of x squared minus 16. How do we handle this thing? Okay, well, in this case, this should hopefully be screaming another one where it's trig substitution. So, oh, let me double check on one thing. I want to make sure I have bounds on. Oh, that's okay. If I do put bounds here, just an FYI, you're going to have to solve for that variable as well. So make sure you're aware of how to handle those bounds. We did one with u substitution, or not u substitution, yeah, with u substitution earlier. Trig substitution works the same. Just make sure you change the bounds if you're going to just plug in right away. Otherwise, wait till the very end and go back in terms of x and solve there. But so in this case, we have square root of x squared minus 16. We talked about the trig substitutions that need to be used. In this case, 16 is 4 squared. So when you go x squared minus 16, you get x equals 4 secant theta. And that means dx equals 4 secant theta tangent theta. Okay. So this integral becomes the square root of secant, or 4 secant squared. 4 secant theta, the quantity squared. Minus 16 times 4 secant theta tangent theta. So this makes 16 secant squared theta. Oh, toss in that d theta as well. So now, what do we have? We have this integral becomes the integral of the square root of, we can factor out the 16, you're left with secant squared theta minus 1. And then we have a 4 secant theta tangent theta d theta. So this whole thing equals square root of 16 times tangent squared theta times 4 secant theta tangent theta d theta. And this becomes, after this part here, we'll get 4 tangent theta secant theta tangent theta d theta, meaning this whole thing is 16 times the integral of tangent squared theta times secant theta. And so this one's actually going to require something slightly different. It looks like a trig integral that we can solve. We can get there, but we're going to need something else, and that something else that we're going to need is integration by parts. Okay, so what I'm going to do is actually I'll start to write what this integral is, but in a slightly different format. So breaking it apart back to what we originally had, tangent theta, then secant theta, tangent theta, right? If we let u equal to tangent theta, that means du equals secant squared theta d theta. Now why would we want to do that? Because, well, dv then is secant theta tangent theta d theta, meaning v must equal just secant theta. So in that case, what do we have? U times v is tangent theta secant theta minus, okay, so it goes v to u, right? And so in that case, we have secant theta secant squared theta d theta. But when you think about it, we talked about secant squared theta. That's just 1 plus tangent squared of theta. So this can be rewritten as have tangent theta secant theta minus secant theta, and then secant squared theta we just mentioned is 1 plus tan squared theta, and then d theta. So at the end of the day, we get that this, however crazy it looks, I'll condense it back to what we had recently. Tangent squared theta secant theta should equal tangent theta secant theta minus the integral of secant theta d theta, and then minus the integral of secant theta times tangent squared theta. Well, multiplication we can write in any order that we want since they're multiplied. So that's tangent squared theta secant theta d theta. Okay, so notice though we have this is one of the same thing, so we got to add this now because it's a minus sign in front. We got to add it over to the other side. So we have 1 and 1, one of these and another one of these. That makes 2 of those integrals. Tangent squared theta secant theta, oops, need the d theta. So that should equal tangent theta secant theta minus the integral of secant theta d theta. All right, so now let's make that transition. Divide both sides by 2, and what we're left with is the integral of tangent squared theta secant theta d theta equals 1/2 times tangent theta secant theta minus the integral of secant theta d theta. Now you might say, oh, well, wait a second. We haven't figured out the integral secant theta d theta. Well, you can. If you want to see me work this out, it's not too bad. You just got to remember, you multiply both top and bottom by secant theta plus tangent theta in the numerator, and then secant theta plus tangent theta in the denominator, and you use a u substitution to get this equaling the natural log of secant theta plus tangent theta plus some constant c. So when we write this, we can rewrite that integral of secant theta tangent theta d theta as just natural log of secant theta plus tangent theta, and then we can always toss in the constant c. Okay, so now we're ready to rock and roll. This equals, then going back to our original, this is 16 times 1/2 times tangent theta secant theta minus the natural log of secant theta plus tangent theta plus constant c. Now you might say, oh, we're done, everything's hunky-dory. Well, not quite. So the thing that we have left is we got to convert all the thetas back into the x's. Okay. So in order to do that, what do we need to have happen? Well, we have secant theta. X equals 4 secant theta, so that means secant theta, if you divide both sides by 4, equals x over 4. Okay. So that means, in terms of the x value, that should be the hypotenuse. The 4 should be the adjacent. And that means this should be the square root of x squared minus 4 squared, which we can also rewrite 4 squared as 16. Okay. So notice we have the secant theta listed as x over 4, so that part's not going to be hard. So when we simplify this, you get 8. Now we need to figure out tangent theta. Well, that's not going to be too bad either. So tangent theta, looking at this triangle over here, that's opposite over adjacent, so that should be the square root of x squared minus 16 all over adjacent side, which is 4. So this becomes 8 times the square root of x squared minus 16 all over 4 times secant theta, which is just x over 4, minus the natural log of secant theta, which is x over 4, plus tangent theta, which we just saw is square root of x squared minus 16 all over 4. Close that off. Close off the parentheses to be multiplied by 8, and then put a plus c, and that is dun 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 dun, dun your final answer. Okay, so that's a nastier trig substitution. Just wanted you to be aware of what's lurking out there, how to handle them. All right, so now moving on to this partial fractions. How do we handle these type? Well, the partial fraction decomposition of stuff of this nature, you get 9x squared plus 11x plus 7 all over x times x plus 1 squared. So what does this equal? Well, this should equal, one of the possibilities is a over x. Well, another possibility that most people jump to is the b over x plus 1 squared, but you got to build up there. So it goes b over x plus 1 plus c over the x plus 1, the quantity squared. So now when you multiply by that common denominator of x, or the common denominator we want, x times the quantity x plus 1 squared, what we're left with is 9x squared plus 11x plus 7 equals a times the quantity x plus 1 squared plus b times x plus 1, okay, plus c times x. Okay. Now here's where things get a little cooler. We have x values, so the first case we'll do when x equals -1. So notice that makes 9 times -1 squared now, plus 11 times -1, plus 7 equals a times 0, essentially. B times -1, but times 0, so plus b times 0, plus c times, that's a c, don't let your eyes fool you, times -1. Okay, so what does all that make? Well, 9 minus 11 is -2, plus 7 is 5, so 5 equals -c, meaning c equals -5. Okay? The next one we can get is when x equals 0. This one will be a little bit easier. You get 9 times 0 squared, plus 11 times 0, plus 7 equals a times 0 plus 1 squared, plus b times, that'll be 0 there, and plus c times 0 there. Okay? Now, keeping that in mind, what do we have? Well, this makes 7, and then equals a times 1 squared, so it equals a, and that's our solution for that part. So now, last but certainly not least, we can't plug in 1, we can't plug in 0. So what happens is, we actually have to distribute here. This is, notice we get ax squared plus 2ax plus a plus bx squared plus bx plus cx. Okay, so probably the simplest one for us to deal with, notice, is the x squared terms. You have an x squared term here, you have an x squared term here, and then you have an x squared term here. So what we can do is we can use 9, and then all of them have x squared, so you can kind of drop the x squared. 9 equals a plus b. So that means that a equals, well, we have a equals 7, so 9 equals 7 plus b. So that means our b value is equal to 2. Okay? And we can kind of verify that if we go let's see here. We have cx would be, c is -5, b is 2, so that would make -3, and then 2 times a is 14 minus 3 is 11. So I was just verifying the x term works out just fine, and so we were good on that. So what this tells us, though, is that our integral, we have a being 7, so that's 7 over x, b being 2, so that's 2 over x plus 1, and c being -5, so that would be -5 over x plus 1 squared. So this sets us up for our integral. This will be a lot easier to deal with. This is 7 over x plus 2 over x plus 1 minus 5 over x plus 1, the quantity squared. Now with those three denominators, notice if we set u equal to x plus 1, du equals dx, there's really not much difference between that and just how the x works. So really, you're going to get a natural log involved in that one as well. If you want to see the steps, let me know. I'll be happy to show you. But you get 2 natural log of x plus 1 in that case. Now on this one, the 5 over x plus 1 squared, the way to write that, you can consider that to be x plus 1 to the -2 dx. And then if you do use u equals x plus 1, then you get du equals dx, so you get u to the -2, so meaning it's negative u. So this goes minus a minus, and then it'd be 5 over x plus 1. Okay. And if we simplify that just slightly, that was just our side work. So you get 7 natural log of x plus 2 natural log of x plus 1, and then plus 5 over x plus 1 plus c. So hopefully you're starting to see how all these basically set up the partial fraction decomposition. The rest is just the u substitution stuff, if need be. The focus is on the partial fractions, that decomposition. The rest is the Calc 1 material, which can be tricky at times too. So for our last one, find all values of p for which the following integral converges. You have 1 over x, 1 divided by x, and then a natural log of x raised to the p power down below. So when we look at this, the first thing we can kind of do is set up an improper integral. You get limit as t approaches infinity of e and then a t, and then it goes 1 over x, and then we have natural log of x raised to the p. Now this might be a little bit crazy, but if you set u equal to natural log of x, and du then equals 1 over x dx. Notice you have the 1 over x sitting out there, and then a dx right in here. So all we need to do is change our bounds. This is the limit as t approaches infinity of natural log of t, here's our new bound, and this is natural log of e, which we should know, but if you don't, that's okay. 1 over u to the p du. Okay, so natural log of e, by the way, is just 1. So notice this becomes limit as t goes to infinity of, probably an easier way for us to write this would be u to the negative p. And so then you can see that this is going to be u to the negative p plus 1 all over negative p plus 1, evaluated at 1 in ln t. So this then becomes, plugging those in, limit as t approaches infinity of natural log of t raised to the negative p plus 1 over negative p plus 1, and then minus, you plug in 1 into that, you're going to get just 1 over negative p plus 1. Okay. So the real trick on here is we need this. Since it's going to infinity, this must go to 0. Now, how do we do that? What's the method for doing that? Well, going a little bit, inspecting a little bit closer, it's all dependent upon that exponent. So that exponent, what must happen? Well, you need negative p plus 1. What would send this thing to 0? Well, you need that natural log of t. If it's going to infinity, you need it in the denominator. So in order for that to be in the denominator, you need it strictly less than 0. So notice if we solve this inequality, we get p is greater than 1, and that is our final answer. For all values, find all values of p for which the integral converges. It's when p is greater than 1. Now you might be concerned about this last part, but notice there's nothing going to infinity there. There's just a p value. So as long as p is greater than 1, you got this thing converging. Okay. That's going to pop up later on in the semester. We're going to determine, basically we need it to converge to 0. And how fast are things converging to 0? That's what's happening here. It's converging fast enough where this this infinite improper integral actually goes to a finite amount. Okay. I don't see any more questions, so I hope you all do well on that upcoming online exam. If you do have some questions, you can shoot me an email. I'll be happy to answer. And then also post in the YouTube live questions, and I'll be happy to kind of address them that way too. So best of luck. Hope all goes well, and I hope you have a good rest of the week.